We're going to look at the last thing here in differential equations, which are logistic models. And so these are related to but distinct from the exponential models you would have seen previously. So a logistic model, like an exponential models, logistic models have a rate that is proportional to the function itself, but they're also proportional to how close they are to a maximum value, which is known as a carrying capacity. And this happens most commonly in a constrained environment. So most real world problems would involve this because there's, if you think about a field and a bunch of rabbits living in it, there's only so much food in that field. So if there's too many rabbits, there won't be enough food, they'll start dying. So there's some constraint on that population. But the more rabbits you have, the faster they'll grow, kind of the rate of change will grow. So this is what we'll end up looking at here, is how we kind of balance those two properties. And so the general form of the logistic model is the change in population divided by the change in time, or the derivative, the rate, is equal to some rate constant times the population times 1 minus P over K, where this K is the carrying capacity. So what you can think about it here is it's the rate times the population, just like an exponential model. But then it's also multiplied by this correction factor that says how close are we to our carrying capacity. So if our population is at our carrying capacity, if P equals K, we get 1 minus 1 or 0, so it means if we're at our maximum population, then we have no more growth because it can't grow anymore. If we're above our population, like if P is bigger than K, then this is 1 minus some number bigger than 1, and we have our population shrink until we get to our carrying capacity. And if we're somewhere lower than our population, like if we're at 0, or almost 0, then we have basically 1 here, and it grows at an exponential rate. So what you end up seeing with this is a graph that looks something like this S-curve, where if you're really low, you have an exponential growth. If you're really high, you have this flattening off to 0 growth. And technically, if you're above the population carrying capacity, you have exponential decay to the carrying capacity. So let's solve the general form. And this is solved by using separation of, or sorry, what's the word? This is solved with partial fraction decomposition, along with separation of variables. You don't need to necessarily know how to solve this. The AP test tends to just ask kind of basic understanding questions about this, but it is good to be familiar with it so you can kind of keep an eye on how we solve, or on how to work with these. So I'm going to start with my dp over dt equals rp times 1 minus p over k. So I'm going to do something here by basically combining all of this to have a k on the bottom. So that's going to give me r times p times k minus p over k. And that's just finding common denominator in this fraction here, k minus p over k, and then rearranging as such. So now I can separate my variables and have dp times 1 over p times k minus p is equal to r times dt, sorry, r over k times dt. Integrate both sides, and I get r over k times t. Actually, no, I don't want to move it this way. I want to move the k to the right side with everything else. So that will give me RT, sorry, plus C. And on the right side, I'll have the integral of K over P times K minus P dP. Using partial fraction decomposition, and you can verify this yourself if you wish, we end up with the expression, the integral of 1 over P plus 1 over K minus P. Again, you can go check that yourself if you wish. That's just from partial fraction decomposition. We get natural log of P plus natural log of K minus P times -1 is equal to RT plus C. So that means we get natural log of P over K minus P is equal to RT plus C. Then we get the not natural log, we want to simplify it. So P over K minus P is equal to E, a constant, times E to the RT. P is equal to CE to the RT times K minus P. And I'm going to skip past the algebra because it's not particularly interesting. It's just a matter of consistently rearranging and solving and blah, blah, blah. And we get P is equal to eventually the initial population times K e to the RT over K minus P plus the initial population e to the RT. If you want to go through this with me, we can, but it's basically a lot of algebra, then saying P0 is equal to, or occurs at t equals 0, P of 0 is equal to P naught, plugging those in to get the P naught. It's a lot of work. It's not particularly important. Typically, they just ask you to work with the differential equations, but we'll kind of look at some of these examples in the next video.